Looks like it's time. So welcome everyone. Who was here for my talk 2 hours ago? A few of you? Okay. So there's a little bit of overlap. I talked in that talk about a little bit about vector databases and embeddings. I'm going to go deeper into that topic in this talk. We're going to do it in the context of images instead of text, but it still applies. So welcome everyone back, or welcome to, depending. This is modern problems require modern solutions. Finding your meme twin with embeddings and vector databases. At the end of this, I have a demo where we can look into the camera and it will take your photo and it will tell you who your meme twin is. And so I may get some volunteers from the audience if we have time. That said, I've got about an hour's worth of material. I only got 45 minutes to do it in, so I may skip a little bit in the middle or at least go a little bit fast. To be completely honest, the middle was there because without it, the talk's too short, but with it, the talk's too long. What are you going to do? So my name is Royse. I'm a developer advocate at Redis. This is all my social contact information. If you're still participating in social media, which quite frankly has turned into a toxic hellhole, then give me a follow on Blue Sky or X, currently Twitter, currently known as X. And I have a blog at guy.dev. And the relevant thing for all you all is the github.com/GuyRoyce. I've got all of my source code and my slides and everything are out there. So if you want to kick the tires on this demo yourself, run it at home, it's just a Docker, it's a Git clone and a Docker compose up away. So, and this is one of the things that I want to kind of, I got two qualifications here. One is that I'm not a data scientist, right? I'm a developer who uses data science tools. And so my explanations are designed to give us an intuitive understanding. I go out and I learn these things and I get an intuitive sense of them and then I share what I've learned. And so I don't want to pretend like I'm an expert here. This is my understanding of things today. It's possible I may say things that are slightly wrong, but are true enough that it's working for me. There's some things I've simplified a little bit that aren't specific, they're true at a certain level of resolution. So do take a little bit of what I tell you with a grain of salt when it comes to the data science stuff, because I'm not even particularly mathy. That said, I'm kind of on a quest with the data science stuff, as I like to call it, and my demo reflects this, to get rid of this idea that you have to spend money with APIs to do all this stuff. I believe that A, you should not have to plop down a credit card to play with vector databases embedding or any kind of LLMs or AI stuff. You can totally run it locally, which I'm going to do on my 5-year-old Intel Silicon MacBook. And if it'll work on this machine, it'll probably work on yours that has an actual GPU. That you don't have to use Python. You can use TypeScript or JavaScript. You can use your language of choice. I'm a JavaScript, TypeScript, Node, front-end person and back-end. And so I tend to use those tools. The JavaScript stuff's cool because these embeddings that I'm going to show you how to create can actually be done in the browser. So you can create embeddings. I'm sorry, I said the browser, I meant the edge. So you don't have to use Python. You don't have to plop down a credit card, and you can run it locally. And I kind of want to show that those are 3 things that you can do with this technology. I think that's very developer friendly. So, but all that said, I'm a developer, I'm not a data scientist. Is anyone here a data scientist? So, my clicker's not working now. So what I meant to say is that I'm something of a data scientist myself. No, that's an airplane. I thought it was feedback. So you should totally listen to everything I say. I totally know everything you need to know about data science. So agenda for my talk today, I've got 4 agenda items. Is that a lot? Well, it depends on the context. For a talk at a conference? No, not really. For a talk with your boss? Yes. So my 4 topics are, looks like it, my pointer is doing weird stuff here. So we're going to cover, first and foremost, what is an embedding? You've probably heard this term, embeddings, vector databases, that kind of stuff. We're going to talk about what that is, how you can use embeddings, how you can make embeddings, and I'm going to go into more detail than that than I really necessarily should, because I'm going to talk about using convolutional neural networks to create embeddings. Most people are using transformers to do this now, but CNNs will still work, and it's a way to help understand the concepts behind them. And then we're going to have I'm going to show off the code and do a demo, and we're going to find out who your meme twin is. Sound good? Yay. Yeah. Excellent. So let's start with what an embedding is. Am I the only one around here who knows what an embedding is? I actually, by the way, just for full disclosure, I took these images, because these meme images are kind of low res, and I took them into Photoshop and I upscaled them using AI, and I filled in the edges. And I love that the bowling alley scene here, if you look on the right, I decided it needed another gun barrel. I don't know what bowling alleys you go to, but this hasn't been my experience. So in order to talk about embeddings, I want to talk about data. And there's two fundamental types of data that we interact with as developers. One is structured data. This is the data you know and love. It is the numbers and the strings and maybe the locations and just all those things that you could put in a where clause in a SQL statement. This is the structured data we know and love. We're developers. We know how to work with structured data. We've been doing it for our entire careers. The entire industry over generations has been using structured data. This is what we know and love and do. One could argue that a lot of our economy is based on this structured and deterministic data. And then there's the unstructured data. And humans use this stuff a lot, but computers struggle with it. We've got text, and you can do full text search, and that helps a little bit, but it's fundamentally keyword search. But if you want to find, for example, all the text that reference cryptids, like Bigfoot and Chupacabra and that kind of stuff, and you look for cryptids, it would have to have the word cryptid in it. So full text is kind of working with search unstructured data, but it's limited. Things like images. Image processing is hard. A human can look at a picture and tell you whether there's a cat in there or not very quickly. Computers struggle with this sort of work. And audio. Is that a sound of booing or the sound of applause? I need to build that demo for a talk someday. That way everyone could boo me. It'd be great. But this is unstructured data. It's harder to search. It's harder to query. You can't just put it in a where clause and pull the data down. You got to do something else. And we'll get into what that something else is soon enough. Structured data, we know how to deal with it. We've been dealing with structured data forever. What you do with your structured data is you store it all in SQLite. Right? That's what you do for all your company's data? No, that's not what you do? Well, maybe you put it in Access instead. No? Oh, you probably put it in Excel. I was actually at a conference several years ago, and a friend of mine, I'm like, well, ultimately all these old systems are COBOL behind the scenes for a lot of these things. He's like, well, either it's COBOL or it's Excel. So structured data, we know how to do. We store it all in Excel, and then we filter it, right? Yeah, or we store it in our relational database, and we query with where clauses. Unstructured data is harder to get meaning out of. Like a human can look at an image and tell you things about it very quickly. You can read a text and a paragraph and say, what's this paragraph about? Computers can do that as well. That's what embeddings are. It's sort of that extracted meaning out of that unstructured data. So here I have 2 bits of unstructured data. I have some text from a meme. Don't need to debug your code if it doesn't compile. Facts. And then the think about it guy. And so you can take these things and run them through processes and turn them into semantic embeddings, embeddings that extract the meaning or of what's in it in the way that a human would. In the case of text, you might need to summarize it to get it short enough to be able to do something meaningful. You use an LLM to do that. You would go through and you would tokenize it. And by you, I mean software you use would tokenize it and pull out the individual tokens. So these tokens aren't words per se. They're often words, but they're also punctuation, and maybe if it's like an acronym like NASA, it would be all the individual letters, that sort of stuff. You can then create an embedding off of those tokens, and an embedding is simply an array of numbers. It's a vector. And so embeddings are vectors that contain semantic meaning. Vectors are just arrays of numbers. A vector could be anything. An embedding is a specialized type of vector. You can do the same thing with an image. You can transform it to get its resolution correct. You can run it through convolutional neural networks, and then you can extract the embedding. And again, you can get a set of numbers. And this extraction embedding is done with models, AI models, that you give it the data in, and it spits the embedding out. And so this is sort of and magic happens part of the work. I'm going to use these tools that people smarter than I have made that I can use to create these embeddings. But what are the embeddings? What do the numbers mean? Well, you can think of them, and we're going to use a very simplistic example of a vector with two values, an embedding of two values. And each axis in there has some sort of meaning that's significant to the model. The AI has looked at it and says, well, this axis here has, we're going to pretend, has to do with how elderly the person in the picture is. And then the other axis is how alcoholic they are. And then you just get a score from -1 to +1, or sometimes 0 to 1. You can score them differently. We're going to use negative and positive in my examples. And then, and this isn't what the model's using internally. This is made up to teach you all how this works. The model has come up with categories of things that are represented by these axes that is meaningful to it, but we don't necessarily know what they are. We do know that when we give it similar images, we get similar numbers out. So if I give it a picture of a cat, of 10 cats, I've got a lot of numbers clustered in this one area with a score that's kind of high. This suggests that it's a cat. It could be a couple axes that represent cat, because maybe one is animal and one is feline, but we don't know. We're going to pretend that we have alcoholic and elderly to make it simple so we can understand this. And so here we have Leonardo DiCaprio with a coupe glass, clearly an alcoholic, but not particularly old. Another image may come along. This is probably one of my favorite memes, is Grandma discovers the internet. Grandma is clearly very, very elderly. She may or may not be an alcoholic, but there's nothing in the picture to suggest it. The extra ingredients in her pecan pie, however, make me think that perhaps she has been drinking a little bit in the kitchen. But so Grandma's got different scores here. And what you can do with these is you can turn these images, these sounds, these texts into these numbers, into these scores. And like the embedding model we're going to use in my demo has 512 dimensions, 512 values, 512 things that it has measured on. And you can take these 512 things and compare them to other 512 things, these embeddings, and compare them to other embeddings and see how similar they are. So here we got 3 images. We got Success Kid, we got the most interesting man in the world, we've got mocking SpongeBob, and then I put in my photo and it creates an embedding, and which one am I most similar to? And so you look at the numbers and you figure it out, and oh look, I'm most similar to the most interesting man in the world. And now if I could only convince my wife that were true. So this is fundamentally what vectors, how you can use the embeddings. You can compare them and see how similar they are. The details on how you can compare them are easier to get your head around if you think of them as points, as coordinates in space. And so instead of having just 2 scores, you have an axis for alcoholic and an axis for elderly. Now for the real model, we'd have 512 axes, which is hard to picture because it's 512 dimensions, but 2 is fine. And so on the top left there, you see you've got the little baby with the really big pint and he looks vaguely drunk. That's also one of my favorite memes. What I love about it is he looks so British. I wonder how that's going to go when I make that joke in the UK next week. But he's clearly young and alcoholic. There's Leonardo DiCaprio. You've got the most interesting man in the world. He's a little bit older, so he's a little further to the right. But he's got a bottle of beer in front of him, but he's not like got a cocktail, so he's probably not quite as alcoholic. Down on the bottom, clearly there's young and alcoholic. But you can put these values out on a 2-dimensional plot. You can plot them out in space, in a vector space. And then you can compare them using things like Euclidean distance, which literally just measures how long the line is between the points. It's that simple. The shorter the line, the more similar the things are. Or you can measure the difference of the angle between the 2 points from origin. The smaller the angle, the more similar the things are. Now, in the middle, things tend to be more general, and in the edges, things tend to be more specific, or further out from origin. And so sometimes cosine similarity is the way to go because, Bigfoot is a cryptid, and those are going to be on the same line. So your similarity is going to be real narrow, even though they might be further apart than, say, Bigfoot and a gorilla, which might be closer, but it's not really what you're looking for. So sometimes using that angle is the right way to go because it kind of shows, it takes magnitude out of the equation, and it's this category at this line. And sometimes you want to do Euclidean distance because you just want things that are closer conceptually. And you can also use an inner product, which kind of splits the difference between those. It doesn't have a nice, pretty graphic like I can show, but it tends to split the difference between the Euclidean distance and cosine similarity. Another thing you can do is you can do a range query. So I provided a point, give me everything that's within like 0.1 or 0.2 of a particular location in this vector space. But all we're doing here is basic geometry. Nothing particular, well, I guess cosine similarity is a little bit of trigonometry. And so that's all that embedding is. And so what you can then do with a vector database is you can store embeddings in a database. And so you've got all these embeddings. You've got the success kid, most interesting man in the world, mocking SpongeBob. And you put them into a vector database like, I don't know, maybe Redis. This works the same in other vector databases as well. I've actually looked at other offerings, and they're very similar in the sense that they offer the same capabilities. I mean, obviously, I have to say that Redis is faster, but it is. But you put them into your database. So here we have Success Kid, most interesting man in the world, mocking SpongeBob. And then with that, then you can query the database and say, using cosine similarity as a score, show me the top 5 things that are close to the thing I'm querying. Now you're searching on unstructured data using the meaning in the image. So if I upload a picture of a cat, it will find other pictures of cats because they have similar numbers, because they're in similar places in the vector space set. And then now we have an animation error that I didn't fix in my slides before I got here. When it's in a database, you can then load this into, or you can create an index on this as well to improve performance. You've got 2 choices. You can do a flat index, which is perfectly accurate, but after about 1 million entries, you tend to need to do something more to scale it better. And you've got hierarchical navigable small world, HNSW. Flat, simple, brute force, perfectly accurate, only scales so far. Hierarchical navigable small world creates basically little flat indices for a subset of the points in the vector space. And then it finds one that's nearby for whatever your query, and then that point then feeds down to another layer of points, and then you can search that one for ones that are close to that, and you drill down through the layers until you find something that's close. This can use more memory or be less accurate or be slower or faster, but that's all tunable. But it does give you an approximate accuracy. It's not as accurate as flat, but it scales much better. I have a link at the end of the talk to a demo, a benchmark that we do a benchmark on a 1 billion vector database in Redis. I don't know what those 1 billion vectors were of. Probably cat pictures from the internet. So using this technology, you can get, I got 3 basic use cases here that you can use this sort of vector database and embedding technique with. One is semantic search. Semantic search is kind of the one I talked about already. The idea is that you have in Redis, in this case I got a bunch of text embeddings, just the messages of memes. Deletion is 100% file compression. TypeScript is just JavaScript for C# developers, changed my mind. And code doesn't compile, compiles it again. And so you store these memes in Redis, you store the embedding of the text in Redis, and then when someone wants to search, don't need to debug your code if it doesn't compile. We run that through a model to create embeddings. And then we go out and sorry, I thought there was one more step in the animation there. And then we go out and we just match. We find the best embedding matches, the top 5 or the top 10, and return those. And we'll find similar things that are semantically similar. So this is all a vector database does. The AI has already happened by the time it gets into the vector database. The vector database is literally taking these points and saying, draw a line. Oh, that's the shortest one. And that's what it's doing. It's indexed it to make it all performant and everything, but that's ultimately what it's doing. Semantic caching is an interesting one. And we actually have a product that we released recently around this. But the idea of semantic caching is that LLMs are expensive and slow. And if people are asking similar questions over and over again, it'd be nice to just return a cached answer. So Grandma is asking, can you explain to me what a dank meme is? And we have an LLM that knows about dank memes and can answer these questions, but perhaps has answered these questions before. Someone has said, what is dankness? I don't understand what dank memes are. And so what Grandma does is she asks her question. We create an embedding of that question, and we go to Redis or another vector database and look for things that are similar. And if they're close enough, then we return them. That's a cache hit. We're going to just return the cached answer from the LLM the last time someone asked this question. We're good. If we don't get a hit, we get a cache miss, then we go to the LLM, we ask our question, it generates the answer. We return it to Grandma, and then we put it in Redis to cache it so that the next user that comes and asks what dank memes are can find out without having to hit an LLM. So this is really powerful and a great way to reduce your cost with the APIs. The other thing that you can do with this is retrieval augmented generation. This was like last year, all the talks were on RAG. But embeddings can be used. It's not strictly speaking necessary, but it's a great example. So here we have Grandma asking the same question, but the LLM doesn't know anything about dankness or memes because it wasn't trained on the internet, because that's totally how AI works. And so we need to augment its ability to generate text with extra data that it doesn't know about documents. A more realistic example of this might be the LLM, ChatGPT does not know who the customers that are in your customer database. And so you need to retrieve information about those customers and hand it to the LLM along with your question so that it can generate a correct answer. So the way this works is we have a bunch of documents about memes, and then Grandma asks her question. We use the vector embedding to find or retrieve documents that are about meme dankness. And then we hand that to the LLM along with, so that context, the matched documents, along with the question that Grandma asked, and we get an answer back to Grandma. So that's what RAG is. And you can combine RAG with semantic caching. Works really well. So the next thing I'm going to show you is something you shouldn't do. So you've been warned. I'm going to show you a way that you can create embedding models, or at least the theory behind it, using convolutional neural networks. I have a full talk on CNNs that I gave a few years ago. Actually, it's about 5 years ago now, where it's called Deep Learning Like a Viking, where I built a convolutional neural network to recognize handwritten runes. So if you want to learn more in depth about these, you can go check that talk out. I'm going to hit this super quick because I want to get to the meat of the demo here. But I'm going to show you a way to create embedding models, but you should totally just use the models that are out there. I didn't create my own models for this talk. I'm using Hugging Face models for this talk. And so I'm going to do a little bit of first principles here. This is your basic neural network. You've probably seen this picture before, right? This is old school. Got an input layer, just a bunch of numbers. All those numbers flow to the hidden layers, where weights are applied to them to transform them to new values, and then the output is put to the next layer, and the output is to the next layer, till you get an output, which is your answers. And you can think of this as a function. Numbers go in, they trickle through the thing like a Plinko board, and numbers come out. And then those numbers answer your question. It is made up of neurons. Each neuron you can think of as a function as well. The simplest neuron would have a single input, which we're going to call X. It would have a single output, which we would call Y. Real neurons have more, but this is to show. And so if you put something into that, you could plot this out. You could draw a line, right? If you, inside of the neuron, there is a weight, which is done by training the network using back propagation. We're not going to get into that, mostly because I don't know the calculus to explain it accurately. And it's got a weight and a bias, and these are all added together and multiplied. So the weight is multiplied by the input, the bias is added, and you get the output of Y. Now, if you're astute, input, weight, bias, and output, you might notice that this is Y equals mx plus b. It draws a straight line. That's what it does. And the slope determines, moves the angle back and forth like this, and the y-intercept slides the line left and right like this. There's the slope, there's the y-intercept. And these are great, but it means that at its simplest, a neuron draws a line, a straight line. And straight lines don't solve all of our problems, as anyone who drives would know. And so to make our outputs of our neural networks less linear, we use activation functions, which transform that output. There are multiple choices. Mostly we end up on ReLU, but you can use a sigmoid to get a value between 0 and 1, that approaches 0 and approaches 1. You can use a hyperbolic tangent, which is pretty much the same thing except -1 and +1. Or you can use ReLU, rectified linear units, which I think is the most pretentious term ever, because it's really just max x comma 0. If it's 0 or less, it's 0, otherwise it's x. We got a fancy name for it. And this is almost always what you go with. And so a more realistic neuron would have multiple inputs, and you multiply all the inputs, each input times its weight, sum them together and add the bias, run it through an activation function, and get your output. So here is the math of doing that. The inputs, the sum of the inputs times the weights plus the bias yields y, or here, the most mathy thing on the entire slide, I used a little sigma to show summation. So that's neural networks in like 3 minutes, the basics. A convolutional neural network is a special architecture of a neural network that's really good for vision processing. It does other things as well, but it's for vision processing. And what you have is you have an input layer, which is a little two-dimensional matrix, conceptually anyhow, of the pixels that are coming in the image. You've got filters, which are portions of that image that it might match. So this is a line going from left to right, or from right to left, or across the middle, or whatever. And then those filters find matching patterns in the input and map them to outputs. And so if you've got a filter that's looking for circles, then you'll get an output which is a map of where all the circles show up in the image. And then you can feed that map of outputs of where all the circles are in the image to another filter that then finds where groups of 3 circles are in the image, and so on and so on. And it hierarchically decomposes the image until it finds eyes and faces and noses and cats and dogs and trees and memes. You can run these through a pooling layer, which compresses down any noise by sort of like visually squinting. Like if you've got a line that's got a little bump on it, if you compress it down with pooling, the line will get straight again, so it doesn't fixate on that bump. And then you flatten that all out and then run that through a final layer that will make a determination of what's in the image, a classification. To use a CNN for embedding, you just take the flattened output. You don't run it through a classification layer. And these basically become all the features it found in the image with a score. Here's a little more visual way of showing that filtering process. We got input, and so like the filter here, see if my pointer works. There you go. Like that filter right there is looking for horizontal lines. I kind of like that this filter here actually finds the eyes, and so it looks like a pair of eyes staring at you. Anyone know what this image is supposed to be, by the way? It's totally a troll face, yes. To show how the filtering works, this filter goes through and basically pans and scans the image. And see, we got a match, so we map it. We got a match, so we map it. Otherwise, we don't. So that output reflects these numbers, or these values. So you get a map of where all the eyes are at. Behind the scenes, this isn't really pixels, it's ones and zeros. And it's actually not ones and zeros, it's numbers from 0 to 1. And so, but these numbers are running through the math, and they correspond to this equation here. So your pixels are your x, the filters are your weights, there's that little bias thrown in there, and then the output has been run through ReLU on the calculations of all those values. And so that's super quick how a CNN works. Pooling, I mentioned earlier, is just going out and finding out, like we're doing a 2x2 pooling here, and wherever there is something here, we map it out, otherwise we don't. In reality, these are numbers again. And so we're looking at, that 2x2 square in the top left, what's the maximum number, or what's the average number? There's several ways you can tackle this. And that sort of compresses it down and gets rid of noise. Flattening is probably the easiest, is because you take the output of all the pooling and you just flatten it out into one line. And now you've got a list of all the features. And these, again, are numbers. So that was a super quick how the hell CNNs work. and how you can use that flattened output is the embedding because it's the features that it extracted. It's that hierarchical of the circle with the 3 circles to the end of, there's a cat, and then there's a value that says this has got catness to it versus this has dogness to it. So, showed you how to do that. It'd be fun to play with, and as a dev, we're looking at it like, yeah, that looks pretty good. Don't. It'd be fun for a toy. Don't use it in production. Creating your own embedding model is hard, and you need to work with a data scientist to do that. So please do. Okay. So let's go on to the demo portion of this. Chappelle is great. It's amazing how often he shows up in these slides. You all got any more of those vector database demos? So I've got a demo here, and I'm not saying that I'm going to use Redis, but I'm going to use Redis. And so what I've done is I built a thing. I'll show you the architecture here, and then we'll do the demo, and we'll have a little bit of time to play with it. I'll show you the code. But what I've built is, of course, here in the middle we've got Redis, and we've got an image meme loader. And so the meme loader goes out and looks in a folder full of memes, images that I have in the GitHub repo. It creates an index in Redis for those memes saying, this is the title of the meme. It actually gets the title of the meme from the file name. And that's pretty much all. There's like the meme bytes itself, like the actual image itself is in Redis. There's the title of the image, which I got from the file name. And then there's the embedding. And so I create an index that knows how to look at the title and the embedding. I then pull all the memes out of the folder. I embed each meme, and then I write those into Redis with an insert. And those get stored in Redis. Then I've got a little meme client application, which is a little web app that I wrote in Vanilla.js. It's a little messy. Don't look at it. It's not relevant to what we're doing. What I should do, and I haven't done in this demo, is I should do the embedding in the client. I don't. Instead, I upload the image to a server, and then the server creates the embedding. But it would be more scalable if you actually did the embedding inside the browser. And then, so the embedding happens there, and then I add that, or I do a search. I've got a pile of numbers here, and there's a big list of embeddings, or memes with numbers associated with them. Find the ones that are most similar. And then we return that. We call fetch and return it. And that's the demo I've built. So it's a fairly simple architecture. And so let's go ahead and take a look at it. Me when I see a talk, but before the demo. We'll see how it goes. I've had issues with my webcam. God, I'm old. But with the camera on my MacBook when I'm presenting, which is awkward. But it's always fixed when I unplug the HDMI and plug it back in. So we'll see what happens. But let's go ahead and get this demo going. Okay. We there? That looks good. Okay. I'm going to show you the code first. So here's the code that does the embedding. All 15 lines of it, including spaces and comments. So here I am bringing in Hugging Face transformers. Hugging Face transformers will download a model from Hugging Face and then cache it locally. So I do need the internet a little bit because I didn't pre-download it and tell it to use a pre-download one because I'm lazy. But it's already been downloaded in my case, so it works. So Hugging Face transformers is just a library that will create transformers. You can do all sorts of things in browser or in Node, including creating embeddings. I set up a pipeline. And so this pipeline is for the purpose of image extraction. And so what this does is creates a pipeline of transformations. And I give it an image through a URL. That could be a file URL or a web URL. Or it could be a data URL that actually just contains the bytes of an image. And it will resize it so that it's square for the model that it has, and then do all the transformations needed to do it, and then send that to the model, and then it will spit out the image embedding. And so this sets up a pipeline to do that. We call embed. I got a little embed function. Here's the path to the image, the string. And then I call the extractor, get a tensor out. In the tensor there is all 512 floats to represent that point in space that is the embedding. I need to get that as a raw byte buffer to put it in Redis. And so I got to get the raw buffer as a uint8 array. And then because I'm using Node, I got to convert it into a Node buffer, which is how you write binary data to Node using Node Redis. So I got one buffer to another buffer, which is a little awkward, but it's just plumbing. And then I return that buffer, and that's it. That's the entire function. I now have an embedding that I can search Redis with. And if I go into here, this is my query. So I've got the search query of star, which says match everything. And then I got my vector query saying, get me k nearest neighbors, the closest one, looking at the field embedding, which is a field that's being stored in Redis. And then here is the embedding that I pass in a $blob. And it just concatenates these together to put them in parentheses with a fat rocket and then square brackets for the vector query. And then it's just a matter of setting some search options here. So here's my dialect 2. My parameters is my blob. This blob here corresponds to this $blob up here. So that's my embedding. I'm passing it in because it's bytes. I can't just make it part of the text command. And sort it by the embedding score and return the title and the embedding score. Then we just call ft.search with the index and my query and those options, and it will return me a document with that embedding. So this isn't, a lot of this code is plumbing code to take the inputs and outputs of Redis into things that are kind of stripped down a little bit, a little simpler. Because you got a general tool, I'm using it for a specific case. So it's just plumbing code. But the actual core functionality here isn't particularly complicated. So yeah, let's take, now I can show you, this is the code to create the index. So here we create an index, we give it a name, and we say the title is a text field and the embedding is a vector field. The algorithm is flat versus hierarchical navigable small world. The data type is a float 32. The dimensions, there are 512 dimensions in our vector, and that's a feature of the model. That's just what the model does, and so we need to align with that. And then a distance metric is cosine, similarity, Euclidean distance, those sorts of things. And we're doing this on hashes, not JSON documents. So that's the relevant code, and all this is out on GitHub. You're not going to remember the code anyhow. The impression I want you to take from the code is just that this is knowable. It's not particularly arcane or cryptic. And using the embedder in particular is super easy. So let's go ahead and see if Docker compose up works. Please work. Come on, ice cream. Okay, this happened the last time, and then I ran it again, and then it worked. I don't know why. It has something to do with not being on the network. I don't know. And see, it's actually creating the embeddings in real time of my 72 memes. So there we go. It's all embedded up. If we got actually into Redis Insight, I wasn't planning on doing this, but let's take a look at Redis Insight. Redis Insight's just a GUI client, which is unfortunately in dark mode. You can see that these are all the memes. So here's Ancient Aliens guy. There's the image bytes. You can see it say JFIF. And then there's the actual embedding, which is just binary data, and then Ancient Aliens guy. Go to this one here. We can see that that is a PNG, et cetera. I don't know how readable that is. Apologies. But the point being here that you can see the actual data is in Redis. It just loaded it. So let's go ahead and actually try the demo. So we'll go to localhost. I used to work with this guy. He aliased localhost on his machine as lolhost, which I thought was terribly clever. So there we go. The camera's working. Does everyone see that? Okay. Let's see who I am. So we'll go. So the way this works is you smile or not. Take your photo. Hit use and see who I come up as. Who do we think it's going to be? So I get one of two things. I either get the most interesting man in the world, which is very flattering, or I get the dad from American Choppers, which is probably more accurate. And it actually seems to mostly depend on the color of the background. And so this is probably going to come up as Paul Sr. Yep, it did. We can change to use inner product instead. I think, let's go, I'm not sure which one it uses by default. Let's just try it again. With cosine similarity, There I am. Let's try Euclidean distance. Yeah. Let's try inner product. This could be funny. They're all the same. Sometimes inner product will come up as grumpy cat because it's just all hair. But so what's happening here is I'm literally taking a photograph, sending it over the wire to my server. It's turning into that embedding, and it's doing the quick search. It says, can I get a volunteer from the audience? Come on up. Let's see who you are. We'll do a couple, and then I'll get back to the slides. All right, let's see who you are. I will warn you that Kombucha Girl comes up a lot.
I make my own kombucha, so that's really funny.
That sounds perfect. So go ahead, stand here in the, and you want to be centered because it crops it. There we go. Let's see what we get here. Yeah. Well, that was inner product. Let's try cosine similarity instead. Let's try it with the different models, or the different metrics. There we go. Fantastic. I don't know if it could be any better than that. Ermigerd Burks.
Okay.
And so all this code is out on GitHub. Does anyone else want to give it a shot? I'll take one more and then I'll finish the slides. I will tell you that if you're a middle-aged white guy, you're going to come up as either the world's most interesting man or Paul from the American Chopper. So that's probably what you're going to be, Greg. Come on up. The camera's following you, isn't it? There we go. Let's see what we get. Yeah. Let's go.
Twins.
Yeah. Separated at birth. Let's try another one here. There we are. That's more like it. Yeah. I concur. It's just you're the most interesting man in the world.
But when I do.
Yeah. Now the AI camera is going to follow you again. Thank you very much, Greg. Okay. Well, that was fun, wasn't it? Like I said, you can pull this code down and literally, I did Docker compose it up. That's all you have to do if you have Docker going, ready to go. It'll just work. So let's get back to the slides here. They're somewhere in here. Where do my slides go? There they are. I just got a couple other bits and bobs here. Should end right on time. So if you want to play with this stuff yourself, the code is out there. You can scan this QR code. It has my slides. It has the code, has everything you need. You can just up and running with it. This QR code is totally reliable, take you where you need to go. It will never give you up, nor will it let you down. If you're interested to learn more about Redis, and I hope you are, you can go to redis.io. There's a whole bunch of stuff. Redis 8 just came out. My demo actually isn't using Redis 8 because it literally came out yesterday, and I just haven't updated it yet. But you can go to redis.io and learn about that. We've got university courses, not like university courses, but like courses online that we call Redis University. I did a lot of the Redis, intro to Redis stuff myself, so if you want to learn more about Redis fundamentals, you can listen to me tell you all about them. So that's at university.redis.io. And we have a Discord server where you can go if you have any questions at discord.gg/Redis. And so, and I'm the admin there, so if you ask questions, there's a good chance that I'll be answering them. But, you know, read the manual first, please. And this is just a link to a blog post just to talk about the performance that you get out of our vector search capability. I mean, it's a benchmark, so there is a grain of salt to be taken with any benchmark. But some of the numbers are pretty significant. We did a test with 1 billion vectors and just got numbers. So some of the competitors we just blew out of the water. Others a little more competitive, but overall, for a vector database, it's one of the top performing ones in the world, if not the best. So that's what I've got. My name is Guy Royse. Give me a follow on all the socials. Go to my blog at guy.dev, get the code at github.com, and thanks a lot.